Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
From the talk, I think several of you know Babak already, because this is actually the last day of his 12-week internship. This is not his final internship talk. He's actually going to talk about some research that he's been doing for his PhD at the University of Waterloo. For his internship, he's been collaborating with us and the University of Manchester on understanding using machine learning techniques in info.net to try to understand childhood asthma. And if you're interested in his end of internship talk, that will be Friday the 17th, probably in the morning. Anyway, Babak's going to tell us about some automating NMR analysis of protein structure.
Thank you so much, Chris. So good morning. Thanks for coming. I know it's a different topic from what you have been doing. Today I will talk about the contributions we have made in automating protein NMR process. This is a joint work with a bunch of people at our lab at the University of Toronto, York University, and between different departments. So the outline of talk is that I will just give a brief motivation about why we are so interested in NMR. And I will give a brief background of NMR physics, what is the NMR phenomenon, and I will give the core concept behind NMR. Then I will talk about the contributions we have made, different modules we have created for NMR, and finally I will draw the conclusions. So the most important question is that why protein structure? Why we need the structure of proteins? So DNA is like a hard disk. It's information carrier. But protein is the functional molecule in metabolic interactions. So if you want to understand the function of protein, its biological role, we need to know its 3D structure. A very promising research area is structure-based drug design. So many new modern drugs that you see for treating horrible diseases like AIDS, cancer, and flu, which kills thousands in North America only, are designed using the 3D structure of protein. This is Tamiflu, which God knows saved how many lives from flu. And why NMR? Because there are a few major methods for determining the structure of protein. For example, X-ray crystallography. The most important benefit is that you determine the structure in its native state, in solution. In X-ray method, they have to crystallize the protein and analyze the electron diffraction pattern. So there is no guarantee that protein in solution is the same as when it's crystallized, the structure. We can use NMR to study molecular dynamics of proteins. We can analyze the folding pathways. And very promising aspect is that we can use it for drug screening. So one of my friends at Waterloo what they do is that they have a protein, they apply different drug-like molecules, and the protein changes conformations a little bit. So all of those structures, they will have the same structure when crystallized because the change is minimal. And it doesn't last so long. But in NMR, we can capture those slight change in the conformations. And lastly, why NMR automation? NMR is cumbersome. So if you go to an NMR lab, you see many people, usually poor postdocs, sitting behind huge monitors, looking at different data sets, spectra. It takes 6 months. I've seen horrible worst cases of 1 year to find a structure. Although there are several software available for speeding up, all of them need excessive human interaction. And human expertise is not cheap. So now, on the history of NMR. NMR has 6 Nobel Prizes. It's amazing when you follow the evolution path of an idea from a single phenomenon for a single atom to becoming one of the most advanced technologies in the modern era. So what is NMR? NMR stands for nuclear magnetic resonance. If you put an atom with non-zero nuclear spin in a magnetic field, it starts to precess around the direction of the magnetic field. The frequency of precession is called Larmor frequency. So this is boring, okay? If you put an atom in a magnetic field, it will precess. But if you put a molecule in a magnetic field, because different atoms have neighboring atoms, the neighboring atoms can shield the external magnetic field, and they will reduce the effective magnetic field sensed by individual atoms in molecule. This will change the precision frequency by a little, but that little amount is enough to identify single atoms in a huge biomolecule. Because this precision frequency depends on the strength of magnetic field, even on the same model of the same device, the magnetic field is not the same from machine to machine. So what people do is that they usually normalize the precision frequency and call it chemical shift. Omega 0 is usually a reference frequency that is always easy to measure, and it's the free state, the precision frequency of the atom in free state.
Does that shift depend upon the angle between the molecule structure and the magnetic field?
Yeah. So it depends on the local electron density. For example, electrons in metal groups, they will sense more magnetic field because the magnetic field will be amplified by the surrounding atoms.
But what about the orientation of the molecule relative to the field? Does the shift vary with that, or does it just depend on the local electron density to the direction of that?
No, orientation of, because the magnetic field that's applied, it will align all the tiny magnetic dipoles into the direction of its field. So all of them are aligned. That's why, I mean, because the difference in shift of one atom is so tiny, nobody can measure. Because we put a huge number of molecules and all of them are aligned, we can measure the shift. So I think like somebody in 50s, he had this idea and he was thinking, okay, now we have a very interesting feature. We can label each atom in a molecule. So how can we use this? I mean, and then it comes Albert Overhauser. He discovers nuclear Overhauser effect. What it does is it detects, I mean, in a nutshell, it detects when 2 hydrogen atoms are close in space. So from past, we know that we can identify which atom has what chemical shift, and now we can know which atoms are close together. And this is the history of NMR. You have a set of distance constraints between some hydrogen atoms, and your task is to build a structure from these distance constraints.
So it's a problem where when you find a solution, it's obvious you found a solution, but you've got a combinatorically big search space.
Exactly. And because of all the noise and artifacts in the input data, you usually have vague constraints. For example, you know that the distance between hydrogen 1 and 5 is 5, or between hydrogen 1 and 10. But you don't know which. That's why it makes NMR so complex.
You mean there exist 2 hydrogens in this structure with distance 5 between them?
No, just one. One of them is completely false.
I'll see when.
Okay. Yeah, let me give an example. So, for example, assume that I tell you the country I have in mind is a German-speaking country. you don't know which country I mean. It can be Switzerland or Germany, Austria. But I will then tell you that it's a port city. It has a port city, so then you will know it's Germany. So we will use this ambiguous information to infer deterministic information. So I will use these terms a lot in the talk. Peak is just a vector of chemical shifts. And each coordinate corresponds to a specific type of nucleus. An NMR spectrum is a set of peaks. You consider a set of peaks and put a bell-shaped function, for example, Gaussian, at each peak location. So this is a real NMR spectrum, which we have cleaned all the noise because they are really very noisy. You can assume that it's the PDF of a multimodal Gaussian distribution. And our job in peak picking is to identify the modes of this distribution. Okay, so now back to what we have done. As I said, NMR is labor intensive. I mean, on paper it should take 6 to 10 weeks. In practice, it usually takes a few months. So protein NMR has 5 important steps. The first step is we have to replace the atoms which are not magnetic with magnetic atoms. This is done in wet lab. We have no control over it. It takes time. And then it's collecting NMR spectra, which again is done by NMR spectroscopists, and we don't have any control over it. It's not a computer science problem. After having NMR spectra, we have the peak picking. We have to identify those vectors of chemical shifts in all NMR spectra. NMR spectra are usually huge. They are in the range of gigabytes because they measure these chemical shifts in a tensor of like 1,000 by 1,000 by 100, for example. So for peak picking, we have designed and developed Picky. And the next step is to assigning these chemical shifts in these peaks to atoms. We have to label atoms with their corresponding chemical shifts. For this task, we have IPASS. IPASS is our assignment program. Then we need to find the distance constraint between hydrogen atoms from the NOE experiments. For this task, we have Success and Connor. Success is a program that predicts the secondary structure of a protein from sequence information and the chemical shifts from the IPASS. And also we have Connor. Connor is a method that identifies the true distance constraints from a set of ambiguous distance constraints using a random Markov field method. And after having the distance constraints, we need to compute the structure of protein. So for this task, we have 2 options, 2 modules. One is Falcon NMR, which is based on fragment assembly. The other one is the SPROS, which is based on semi-definite programming. This one is still experimental and is being developed at the moment.
You just run strictly in sequence? Or
Yeah, exactly.
You only know how to go back and repeat the process.
I mean, that will be really good. I mean, that's the future work. I mean, so, for example, as I said, Success uses chemical shifts to predict secondary structure. But IPASS uses raw predictions of secondary structure to label chemical shifts. So we can iterate over this process. So Picky. Picky is really picky, and it's a program designed to identify peaks in a wide range of NMR spectra. When we started to design Picky, we looked at, I mean, we never intended to implement and design all these modules. We look at the off-the-shelf methods, and we saw that they all need massive human interaction. They have lots of parameters, and they need an expert eye to identify fake from real. So we designed the PICI to be fully automated, no need for human interaction. We wanted it to be fast and efficient and be reasonably accurate, because you can never be as good as a human being for identifying peaks. And we designed it to be modular and could be integrated into our larger pipeline. And actually PICI is all of these. PICI is implemented in C++, and it's very fast and reasonably accurate. PICI has 4 major modules. NMR spectra, when they arrive, they are a mess. So for example, your spectrum is supposed to be all positive values, and you see a huge negative component in the middle. There are different sources of artifacts and noise.
So this spectrum is, you say, 1,000 by 1,000 by 100?
Yeah, it's a tensor.
Well, yeah, 3D object.
Yeah.
And is that itself the raw output from the NMR machine?
Yes.
Or has that been DFFT or?
Yeah. It's so the original signal is in the time domain. They take the Fourier transform, and what we have is in frequency domain. Yeah.
Okay, so the input is that, and the output is a list of peaks or something.
Yeah, exactly.
And of course, in principle,
Mm-hmm.
we would simply explain the raw pre-IFFT signal as a generative model.
Yeah.
But that would be insanely difficult, so we're going to do this intermediate step where we take out some points.
Yeah, exactly.
Right.
So previously, people believed that in NMR spectra, we have 2 noises. One is a global noise, which is the same for all the tensor, all the regions in the spectrum. And there is a local noise. But the problem was that they used a very small sample of points, sometimes as little as 4 points, to compute the noise variance for a local region. So it was very inaccurate. We proposed another model. We said that in NMR, then we have a global noise and we have local severe disturbances. So instead of computing a local noise, we devised some methods to identify local disturbances. So after we remove all the noisy points from spectrum, we divide it into components. If I go back to the multimodal PDF analogy, we divide it into single modes of distribution. And then in order to find the peaks, we decompose each component using SVD for 2D and higher order SVD for higher 3D spectrum. In theory, each peak, for example, Gaussian, should be orthogonal. It should be product of, for example, 3 rank 1 vectors. So previously, people used linear programming to solve this decomposition problem. We used a similar program, and we saw that it's very slow. And we proposed that instead of using linear programming, use SVDs. It's proved to be optimal. And then after finding these peaks, because some chemical shifts are shared between different spectra, we use this information to prune and drop the fake peaks. We also use the information about the shape of the peaks and their intensity to eliminate peaks that look suspicious, that are not supported by other spectra. So here you see oh, it's so bad in here. A sample spectrum. It's for protein YSD0336. And we have picked 91% of peaks. For example, here you see there are some modes which we haven't picked, because, although you can see there are clearly peaks, those are not supported by rest of the spectra.
Is there a way to verify this?
verify, I mean, whether we have made a mistake or not. Yeah. So what we do is that we take the final chemical shift list assigned by an NMR expert, and we synthetically generate peaks for each spectrum. And we compare whether we have made a mistake or we haven't. So that's why, I mean, you cannot do it for a new protein, but for the proteins that you have the chemical shifts, you have verified whether it's effective or not. And most of the time, it's effective and it increases the accuracy. Yes, please.
Is there a difference here? Would you rather pick, for example, more peaks than necessary, or is it better to pick fewer peaks? Is there sort of a decision problem as well?
So because we designed Picky to be, you know, the first module and its result will be fed into IPAS. IPAS is more sensitive to recall than precision. IPAS is quite successful in omitting fake peaks. Yes, please.
So I assume other people have also built such a pipeline, or you the only one? Like, I mean, I'm wondering, like your results on the success rate, how does it compare to what other people have done? Like, I mean, it's now a sequence of steps, but is it optimal, or like is it designed to be fast compared to like good success rate? And
for picking, there are a few programs, but I mean, we couldn't run them. And none of our collaborators were able to run those programs. And the problem is that in their papers, they report no sort of performance measure. No, I mean, it's just, they put a spectrum and say, it seems that we have picked all the peaks. So we couldn't compare with those programs. And usually those programs need, I mean, you pick the peaks, and NMR experts look at the peaks and says, oh, this looks bad. I will tune the noise elimination factor. Now it looks better. So, I mean, there is no way to actually be able to compare Picky with the competition.
So, how many atoms are in this molecule?
90.
90.
Yes. Oh, I mean, you can see, this is the limitation of NMR. If the protein becomes large, it will be very crowded, and usually the center is the most crowded part. So NMR is usually limited to proteins of length at most 200. And for 200, you need to swap hydrogens with deuterium to make it more magnetic. So we tested the whole pipeline and also the individual modules on 4 real protein data sets from University of Toronto and University of York University, sorry. So we tested Picky on 19 noisy spectra, and the recall and precision rates were 91 and 76%. These values are lower bounds because in order to evaluate the performance, we made the synthetic peaks, and an NMR expert, it has, from the experience, he can see peaks that we cannot see. I mean, they predict that there should be a peak at this place. So, I mean, if I wanted to pick peaks, I wouldn't achieve these measures by picking. And Picky is, it's first prototyped in MATLAB, and then it ported to C++. It uses GSL. It's now a plugin to a well-known program called Sparky. It has a GUI and stuff, and it has been downloaded a few times by NMR labs from every part of the world. Okay, now to assignment. Assignment is the process of labeling atoms with their corresponding chemical shifts. The input to assignment program is peak sets from different spectra. So for IPAS, we just took the very common experiments. you can add more spectra, but we only took the most prominent spectra that being collected by a majority of NMR labs. So in order to make the assignment simpler, the chemical shifts that correspond to a single amino acid, to a single residue in the protein, they are grouped together in a vector called a spin system. So each spin system is assigned to a residue. With this definition, the assignment process is the mapping from set of spin systems to set of residues. If the number of residues is n, the number of a spin system is m. M can be smaller, can be larger than n because of all the noise and artifacts. So IPASS stands for integer linear programming based assignment, and IPASS also has 4 major modules. The first one is forming spin systems. Spin systems are usually formed by an NMR expert. I mean, they have a very interesting process. It takes, a few days. They can follow the chemical shifts and form spin systems. To be honest, this module of IPASS has been the most, loved between NMR people because it makes their lives much easier. So we use the graph-based clustering algorithm to cluster chemical shifts into spin systems. Yes, please. You have a question?
No.
Oh, okay, sorry. And then we type these spin systems. We compute the probability that each of these spin systems can be mapped to a residue. The next step is to identify the connectivity information. To make the assignment possible, what NMR people do is that they run some experiments such that each spin system contains information from the residue it's supposed to map and from its preceding residue. And finally, we solve the integer linear programming problem. What is a connectivity graph? So each spin system contains intra-residue and inter-residue information. If two spin systems Sj and Sk can be linked, if and only if their common corresponding chemical shifts match. If two spin systems match, and for example, assume Sj and Sk are linked, it means that if Sj is mapped to Ri, Sk should be mapped to Ri plus 1. So, unlike previous assignment algorithms, instead of assigning single spin systems to single residues, we assign spin system pairs to pair of residues.
I'm missing the significance of a residue. Is it that the atoms are somehow more tightly bonded or something? Is this what's the
residue?
Yeah.
Residue is just like residue 5 is the amino acid at
I think I know
fifth.
what it is. I think I don't know what the significance of it is in this sort of pre-clustering of this grouping of spins. Why is that significant?
Oh. So, because, the peak sets, we have a huge amount of information. We need to somehow summarize it so that the problems become tractable. So we group all the chemical shifts that are supposed to correspond to a single residue. And we call that a spin system. For example,
So is it the case that the interactions within a residue are sometimes stronger than those between residues? And what's the significance of a residue in the context of the shifts?
oh no, it doesn't have anything with the NMR phenomenon. This is just to make assignment process easier. For example, a spin system contains the chemical shifts of its nitrogen atom, the hydrogen connected to nitrogen, the carbon alpha chemical shift, the carbon beta chemical shift. So we put all those chemical shifts in a vector and call it the spin system. So connectivity graph is a directed graph. The vertices are the spin systems, and edges are, an edge is in the edge set if, for example, EJK is in the edge set if SJ is linked to SK. So we made a little modification in the way that these edges are found. We gave them a reliability measure, and we use the NOE experiments. So now we have a set of highly reliable connections and so-so, not so reliable connections. Also, we refine the connectivity graph. This is a conflict because if there is an edge between J prime and K, and also there is an edge between J and K, we know that K has only have one preceding spin system. So one of them is incorrect. So we usually discard the edge with the lower reliability. Okay. Yeah.
If you only don't have one parent,
Yeah.
so this directed graph will have only be a tree structure, is that?
If, that would be true if all the edges, okay, so in the ideal case that's true, but in practice, because some residues, some atoms have the same chemical shifts. Because remember, chemical shifts depend on the geometry of the surrounding area. And protein has some repetitive patterns. So what we see is that we have a bunch of residues with exact same chemical shifts. And they are all as reliable as the other. So we have no way of refining or discarding that edge.
Okay, so you will have some conflicting edges where you don't know which one.
Yeah, exactly. Yeah.
But what you're saying is that there's a true underlying graph, which is a tree.
Yes.
Okay.
So originally, any spin system can be mapped to any residue. But if you look at the protein data bank, and if you collect the statistics of chemical shifts of different residues, amino acids in different secondary structure states, you see that there is a strong correlation between chemical shift and the secondary structure state, the atom type, and the residue type. So we use this information to reduce the number of possible mappings between spin systems and residues. What we do is that we compute the probability that a spin system J can be mapped to residue I. And in order to compute that, we use the secondary structure information from the program Cypred. And what we do is that this probability, which is probability of observing chemical shift Cj for residue type, amino acid type Al, and secondary structure state sigma k, we approximate these probabilities as a non-orthogonal joint Gaussian distribution. So, as I said, the information in spin system Sj, it has two parts. The residue is supposed to map and the preceding residue. So, in previous methods, they only use this part. They just threw away the information from preceding residue. And also, they discarded the fact that chemical shift depends on secondary structure too. After we compute these probabilities, if this value is very small for a spin system and residue, we just drop it. We have a threshold of 1 over 1,000. And if the probability is lower than that, we set it to 0. Yeah.
Is the secondary structure something you're going to know? Something you're going to have to?
Secondary structure is a property that can be predicted with around 85% reliability.
From these experiments or from other experiments?
Yeah. So no.
From NMR experiments? Or just
No, it's from sequence information.
sequence?
So there are some programs that only take the sequence, and I think they are developed in Oxford. They just take the sequence and they predict the secondary structure states. Actually, they don't predict the state, they just give the probability of different states. It's a probabilistic model. So, as I said, we wanted to solve this problem with integer linear programming. Assignment problem has been shown by many people, and we have showed it too, that is NP complete. There is no way to solve it exactly. Although ILP is NP complete, but small instances can be solved very efficiently. So instead of solving a very large ILP problem, we solve many small ILP problems. So using the very reliable connectivity information, those supported by NOE experiment, we form fragments. For example, if EJK and EKQ are both in E, we know that we have a fragment of length 3. We form all these fragments and we find the maximal non-conflicting fragment combinations. We enumerate all those combinations and run ILP for all the combinations and pick the one with the highest score. So this is the ILP setup. At left, you can see the spin systems from S1 to Sm. At top, we have residues R1 to Rn. If the probability of assigning a spin system, for example, 2 to residue 1 is non-zero, we put a note here. We call it V12. And also, for example, if we have V12 here and V21 here, and also we see that in the connectivity graph, there is an edge between these two, we put an edge in here. Each edge has a corresponding weight that is computed from the probabilities that this spin system pair can be mapped to this residue pair. So then the optimization problem is to pick a set of edges that maximizes the overall probability. So for each spin system can be assigned to at most one residue. So the summation of V's in each row should be 1. And also each residue must have only one spin system assigned to. So the summation of V's column-wise is also 1. Only one node can be active. And this is the ILP formulation. We use both Cplex and GLPK, and each iteration takes around 5-10 seconds because the problem becomes very small once you remove the unlikely mappings and you fix the fragments. And we have never seen more than 200 fragments combinations. If we see more, we drop the less likely fragment of the shortest length. And we repeat this process until the number of combinations is less than 200. These are the performance results on the 4 proteins. So Ribro and Mars are 2 programs that report very good results. So we compared with these programs. This is the length of the protein. Max indicates how many residues could be assigned by an NMR expert in 6 months. Spin systems, for example, for TM, our module identified 85 spin systems, and 81 of them was correct. So for all proteins, IPAS outperforms Mars and Ribra. It may seem that, for example, here we have assigned 30 and an NMR expert assigned 60. So it may seem that we are doing bad. But the good news is that IPAS can assign residues in a rigid parts of the protein. Because non-rigid parts they move fast, they change conformation very fast. So their signal in the spectrum is broadened, it's faded into noise, and it's very hard to detect. But for predicting the structure, what we need, in fact, is the rigid core of protein. That's the hard part.
You got
Yes.
3 numbers in each case.
Oh, sorry, my mistake. So on the right is the number of assigned residues, and on the left is the number of correctly assigned residues.
That is correct. That's the expert.
Sorry? Yeah, comparing to the human expert, yes. Okay, so to make the long story short, what we did is that we took the assignment, we used the chemical shifts, and we parsed a fragment data set made from protein data bank. And then we used the fragment assembly program, Falcon NMR, to assemble these fragments into a protein. It generates like 1,000 structures. How to choose the best one? If we use the conventional energy functions, the distance between the predicted structure and the native structure will be too high. So what we did, we designed a new contact scoring scheme that uses the NOE information to pick the best structure. Here you see the structure we have predicted, and the numbers in the parentheses are the RMSD distance between the native structure and the structure we have predicted. So our collaborators, they were amazed when they saw these numbers. It takes them, 2 months to 6 months. For us, 1 day. And the major part is, Falcon NMR, because it has to sample 1,000 structures. It takes so long. So again, it just 1 day and it needs a cluster. So that's why we moved to Spruce or an STP-based scheme. So the current programs, they are based on simulated annealing and gradient descent. The most prominent program is in torsion angle space. And there are some other programs in the Cartesian coordinates. But this is modern era. At the very beginning of NMR, people used Euclidean distance matrix completion. I cannot imagine how much they did suffer because they worked directly on the distance matrix. You made a move and you violate a bunch of triangular inequality constraints. It's a very hard problem if you want to work with distance constraint. So instead, recently with the advent of scientific programming, people use the gram matrix or the matrix that contains the inner products of points. So distance matrix and the gram matrix, they are linearly and closely related. So if you want the D, Euclidean distance matrix, to be a valid Euclidean, we just need to enforce that the corresponding gram is positive semi-definite. That's it. So now we can write our program in terms of an STP problem. And this is really good because in torsion angle space, we work with torsion angles. And distances are expressed in a form of a highly nonlinear function. It's extremely hard to optimize. It's not convex. It has many local minimum. So people use STP. But STP is complex. And practically, although it's n cubed, if n is larger than 3,000, it's not practical. So there was a paper by Volkovics and Lorvain that they say if you see structure in data, if your points contain some clicks, by click I mean a set of points that all pairwise distances between them are known, then you can reduce the dimensionality of your metrics. So in this reduction, this is an exact reduction. These two notions are equivalent. It's not an approximation. So U matrix is known. It's computed from the information contained in the clicks. And Z is a much smaller matrix. This was for disjoint clicks. if you have, so what if you have intersecting clicks with non-rigid? With non-rigid, I mean two clicks that can move, that can change conformation in space with regard to each other. So we took this idea one of Volkovich's student, Nathan Krislock, is my collaborator.
5 minutes.
Sure, I'm done. If you look at the protein backbone, it's not as flexible as it seems. Protein blocks, we have peptide planes. Amino acids are in planes, and these planes can only rotate around these two bonds. So we said, okay, we have the clicks here. We have two-dimensional clicks which intersect at one point, at one hinge. So the Cartesian coordinate system was, from the first day, it was always very complex because you have to add 3 variables for each atom. If you want to add a peptide plane, you have to add 15 more variables for Cartesian and 2 for torsion angles. And that's why torsion angles were always so attractive. For normal STP, you have to add 5. But for the scheme we have devised, you have to add only 2. So by adding each peptide plane, our version of STP is as complex, it adds as more complexity as torsion angle. So we have several different protein families. We can extend this idea and model the side chains. Side chains of amino acid can be modeled as a set of intersecting clicks. If we do that, and if we consider there are 4 different protein families, and if you sample from those protein families and compute the reduction ratio, our version of STP is 3 to 5 times smaller than the regular STP. On average, it's 100 times faster. This is a sample helix. It's only 15 residues. It contains 150 atoms. But the STP metric size was only 50 in our experiment. So now what we want to do is that we saw that these hydrogen atoms, they don't provide much information. In fact, hydrogen atom is so tiny that it's just a little bump on the carbon atom. So we are planning to omit these hydrogen atoms, change the distance constraints corresponding to those atoms, and make a much simpler model which be 10 times smaller than the original STP model. So to finish the talk, we designed and developed a fully automated protein NMR pipeline. We tested on 4 real protein data sets. It produced reasonable results. For future work, as I said, we need to simplify side chains. We need to use the output of success, secondary structure predictor, to improve assignment accuracy. One of my friends is designing a method to take the structure and chemical shift and reassign the chemical shifts. So we can use his program to reassign based on the structure we predict and then iterate. And finally, we need to finalize the Markov random field based constant refinement scheme we have, and it will be done in just a few weeks. Yeah. Thank you so much.
So your future work, is that primarily to make this whole pipeline faster, or are there particular failure modes you want to address, or is it just you want trying to reduce that structure error?
So the major goal is to handle large proteins. Large proteins have a limited number of NOE distance constraints. So we need to grasp to the domain knowledge much more than small proteins. The domain knowledge in STP is the fact that has been ignored by many researchers. The fact that we can use a full-field all-atom energy function to guide the search direction toward protein-like structures. So that's the major goal, for now. Yes, please.
There has also been this NMR spectroscopy.
Yeah.
So instead of doing it on the proteins, or you do it on the more brain, and you try to figure out what happens in the same manner for the larger molecules. So how does it, you said that there are not that many, because my spectroscopy, I guess it's been there for a longer time, and there was algorithms for the kind of group picking and also fitting spectra or smooth spectra or finding temperature or normalization. So how does the algorithms for this problem actually compare to those?
Sorry, you mean mass spectrometry or
Yes. No,
the spikes? Oh, those spikes are in one-dimensional. So NMR at the early ages, everything was one-dimensional, and people were so happy. We solved a molecule with 20 atoms. So why researchers add dimension to the spectra? Because they want to reduce the ambiguity in chemical shifts. If you have only one dimension, it's very possible that many peaks collide and overlap. So now, one of our friends at University of Brisbane, Queen's at Brisbane, he's working on 4-dimensional spectra. And they are using some non-uniform sampling techniques, because a 4-dimensional spectra, if you want to record all the points, it will take years. So they just sample regions with highest entropy. Yes.
Who was first?
Yeah, you're gone.
What was the reasoning behind this sort of stage-wise system? Is it because other people divided into exactly these stages that you also divided into these stages? Or is there another motivation?
Very good question. Yeah, I think from the early days, it was always thought that it should be like this.
Okay.
And even as we follow the tradition, we have a very hard time pursuing our biological laboratories that what we do is actually good. So in order to compensate for that, we added many iterations to make modules interact more. I have the flow chart here somewhere. For example, here is the module we use to predict the structure. So we make different modules interact and iterate so that we find a better structure. But what you said is correct.
Can I ask another question?
Yes, please.
You mentioned that you can take the final structure and synthesize a spectrum from it.
Yeah.
And use it to check your peaks.
Yeah.
Do you use that as as a correction mechanism in this whole process ever? Like a final fine-tuning or something?
Mm-hmm.
You can sort of check whether the synthesized NMR actually matches something you have.
Yeah. So there are some programs that take this structure and they predict the chemical shift. They are not bad, but the accuracy, is around 1 to 2 ppm. And when we check for accuracy of peaks, we use 0.5 ppm. It can provide some insight on the location of peaks, which will be very helpful if we use. But the predictions are not so accurate. But that's something that we can definitely use if we pick a peak which is way over like 5 ppm wrong, then we can use that information to, drop that peak.
But the peaks you showed us were spaced at about 0.1 ppm.
0.1. Yeah?
You had dots pretty much at that
Yes.
spacing. So, but you said you measured the accuracy to within 0.5.
No. What I said is that when we want to measure whether we have identified a peak or not, we have the set of picked peaks and we have set of synthesized peaks. We look, we take each peak from the real list, and we see whether we find a peak which is closer than 0.5. 0.5 is the absolute maximum tolerance acceptable by NMR experts.
But in the image you showed us with lots of peaks, the one about which Marcus asked whether precision or rapport was more important.
This one, yeah?
Yeah. Those peaks, at least in the H, are spaced at, they're 0.5 is the tick distance on the x-axis.
Yeah. So, okay, assume that we want to assign a peak to find the match here. We have a peak here, and we want to see which peak it corresponds to. We compute the distance, we drop all the peaks that are further than 0.5, and from this tree, we pick the closest peak.
All I'm saying is 0.5 is a very big distance.
Yeah, it is.
But the other one is 5.
I noticed, the other one is 5. So
Oh, sorry. In this direction, it's 0.05. But in the nitrogen direction, it's 0.5. Sorry. Because, the range here is around 3, but the range there is around 30, 25.
Okay, I think if you have the time, perhaps we'll take other questions offline. Thank you, Alex, once again.
Okay.